let's consider another example. So let's consider the vector space of all 2 by 2 matrices. So recall that this is an inner product space if we endow this with the Frobenius inner product. The Frobenius inner product is given by the trace function. Okay? So if A and B are 2 by 2 matrices, then their Frobenius inner product is equal to the trace of A transpose times B. So here, we note that matrix A is orthogonal to matrix B because we can compute, or we can see that the inner product, or the Frobenius inner product of A and B is equal to 0. Okay? So the Frobenius inner product, recall, is equal to the trace of the transpose of the first matrix multiplied by the second matrix. So this is the transpose of this. So we want to compute the trace of this product, but in computing the trace, we are only interested in the values of the diagonal entries. So it's enough to compute the entries in the 1-1 position and in the 2-2 position. The entry in 1-1 position is 1 times -1 plus 3 times 3, or 8. The entry in the 2-2 position is 2 times 0 plus -4 times 2, or -8. So the trace, which is the sum of the diagonal entries, equals 0. So A and B are orthogonal. We can also compute for the length of vector A, or rather vector B, with respect to the Frobenius inner product. So the length is the square root of the inner product of the vector with itself. So we take the square root of the inner product of this with itself. That's the trace of the transpose of the matrix multiplied by the matrix. Okay. So again, in computing the trace, we are only interested in the values of the, or along the diagonal. So we can simply compute -1 times -1 plus 3 times 3, that's 10, and 0 times 0 plus 2 times 2, that's 4. So the length is the square root of the trace, or square root of 14. Let's compute the distance between A and B with respect to the Frobenius inner product. So the distance between A and B is the length of A minus B. So A minus B is given by the 2 by 2 matrix with coordinates, or with entries 2, 2, 0, -6. So we compute for the length of this matrix. And again, the length is computed relative to the given inner product. Okay, so we take the square root of the trace of the transpose of this matrix multiplied by this matrix. Okay, so in the radicand, you just need the trace of 2 times 2 plus 0 plus 2 times 2 plus 0 times 0, that's 4. 2 times 2 plus -6 times -6, that's 40. So the trace of this matrix is 44. So the distance between A and B is the square root of 44. Recall that the vector space of continuous real-valued functions on the closed interval 0, 1 is an inner product space with inner product given by the definite integral from 0 to 1 of the product of two functions, two vectors in V. So this inner product that we defined on V enables us to think of a function as an object that has a length and direction. Consequently, we can view problems about functions as geometric functions, or geometric problems. So this is despite of V being an infinite dimensional vector space. So in V, let's take the functions f of x equals x and g of x equals x squared. So we can compute for the length of f. Okay, the length again is relative to the definition of the inner product. So the length of f is the square root of the inner product of f with itself. The inner product of f with itself is the integral from 0 to 1 of f of x times f of x dx. Okay, so the integral of f of x squared dx from 0 to 1. Because f of x equals x, so we just need to compute the integral from 0 to 1 of x squared dx and take the square root. So we can easily compute for the definite integral. The definite integral is 1/3. And so the length of vector f is square root of 1/3. So we can compute also for the distance between f and g. So by definition, this is the length of f minus g. Remember, the length is, or the definition of the length is relative to the inner product. So this is equal to the square root of the inner product of f minus g. But f minus g is x minus x squared. Okay, so this quantity is equal to the square root of the definite integral from 0 to 1 of x minus x squared times x minus x squared dx. So it's the definite integral of this square. And you may expand that before you evaluate the integral. So expanding, we get this definite integral as radicand. And the value of that integral is equal to 1/30. And because we are computing for the distance, so we take the square root of that integral. So the distance between f and g is the square root of 1/30. We can also compute for the angle between f and g using the formula indicated in the first slide. So theta is the arc cosine of the inner product of f and g divided by the product of the lengths of f and g. Again, this is relative to the indicated inner product. So the numerator is the integral from 0 to 1 of x times x squared. The denominator is the square root of the definite integral from 0 to 1 of f times f. So actually, it's the function that we, or the quantity that we solved here earlier, no? The magnitude or the length of f, and the length of g is obtained similarly. So we take the square root of the integral from 0 to 1 of g times g. So x to the 4th dx. And you can check that this quantity is equal to 1/4 divided by the square root of 1/3 multiplied by square root of 1/5. Or the arc cosine of square root of 15/4.